Every electricity generation technology has advantages and disadvantages. For example, renewable technologies such as solar and wind do not produce greenhouse gases but are not always available when needed and can require significant amounts of land. On the other hand, technologies such as coal and nuclear can produce electricity in large quantities reliably around the clock but can result in significant greenhouse gases when unabated in the case of coal or long-term waste disposal considerations in the case of nuclear. Understanding these trade-offs among generating technologies reinforces the importance of having a diverse generation technology portfolio for reducing greenhouse gas emissions while economically and reliably meeting electricity demand. When applied as part of an integrated portfolio, all generation technologies can play useful roles that capitalize on their strengths. This video explores some of the advantages and challenges of both current and emerging electricity generation technologies when comparing attributes including cost, availability and operational capabilities, and environmental considerations. It presents a comparison of technologies at a high level, followed by a more detailed explanation for the assessment of each parameter analyzed for each technology. While the assessments represent the general characteristics of the technologies evaluated, the exact details of many parameters will be unique to the site, region, and/or country in which the technology is being considered. Furthermore, the details around the costs and capabilities of emerging technologies are less certain than those of generation technologies that have been mature and commercialized for decades and reflect expectations more than demonstrated capabilities. Now we will talk about CCS, carbon capture and storage. CCS is a vital technology that plays a significant role in mitigating the impacts of climate change. As the world continues to rely on fossil fuels to meet its energy needs, the emissions of carbon dioxide and other greenhouse gases continue to rise, leading to global warming and other environmental concerns. CCS is a process that captures carbon dioxide (CO2) emissions from power plants and other industrial sources before they are released into the atmosphere. The captured CO2 is then transported and stored underground in geological formations such as depleted oil and gas reservoirs or saline aquifers. This process prevents the carbon dioxide from entering the atmosphere, thereby reducing the impact of greenhouse gases on climate change. The technology behind carbon capture and storage is relatively simple. Hydropower includes conventional hydro, small hydro, run-of-river or river-in-stream, and pumped storage. Construction cost. Construction costs for hydro plants can vary significantly based on the type of plant and its location. Small conventional hydro in prime locations is generally less expensive than pumped hydro storage, which in turn is less expensive than run-of-river installations. Electricity cost. Electricity production costs for new hydro plants are relatively low compared to other technology options. Hydro plants often operate seasonally based on water resource availability, so may have lower electricity output than some technologies, but have a long lifetime, which can offset some of the higher capital costs. Capacity factor. The capacity factor of hydro plants varies depending on water availability and environmental regulations that could prevent the plant from running. Ramping capability. Hydro plants are extremely flexible. Their ability to start up quickly and respond rapidly to changes in load are comparable to natural gas plants. Availability. Hydro plant operation is limited by seasonal flows based on rainfall, snowpack, river icing, and temperature. Operation can also be limited by regulations regarding fish protection. The land area requirements for hydro plants vary with plant type. Run-of-river systems require minimal land area, pumped storage requires an area similar to that of a fossil plant, and conventional hydro requires a significant amount of land for its reservoir system. Run-of-river hydro plants have negligible water loss, but conventional hydro plants with large reservoirs have water losses due to evaporation. There are no GHG emissions related to combustion in hydropower generation. However, GHG can be emitted from the decomposition of organic matter and from bacteria in dam reservoirs. Because there is no combustion involved in hydropower generation, there are no air emissions associated with power production. There are no waste products associated with power production from a hydro plant. The process for permitting a new hydro facility involves review from multiple federal, state and tribal agencies and may take several years. Hydro plant dams are likely to require indefinite maintenance as the structures will remain in place even after decommissioning. Onshore wind includes onshore wind. Construction costs for onshore wind farms are relatively low compared to other technology options. The electricity output of a new wind farm will vary largely with regional wind resources, which will have a strong effect on electricity production costs. Current electricity production costs from new wind farms are relatively low given their construction in regions with favorable wind resources. Capacity factor. The capacity factor of onshore wind is dependent upon the wind resource available at the site. Most wind farms today are built in regions with high wind resources but will vary regionally. Ramping capability. Given proper conditions including weather, onshore wind plants have some ability to ramp up and down for certain durations and magnitudes and have been relied upon to do so in some places to support grid reliability. They can be shut down or turned out of the wind to reduce plant output if needed. Onshore wind plants are available to produce power only when the wind blows at sufficient speeds, which may not correspond with peak demand. Turbines must shut down at wind speeds exceeding their design range, and power production may also be limited by transmission constraints in remote wind-rich areas. The land area required for a wind farm is roughly 85 times larger than the area required for a conventional nuclear plant of similar capacity. However, only 3 to 5% of the land is occupied by equipment, and the remaining land could be used for agriculture or livestock grazing. There is no water use required for power production at an onshore wind farm. Direct greenhouse gas (GHG) emissions. Because there is no combustion involved in onshore wind power generation, there are no GHG emissions. Because there is no combustion involved in onshore wind power generation, there are no air emissions associated with power production. There are no waste products associated with power production from an onshore wind farm. Permitting for onshore wind takes less time than large-scale thermal plants, with zoning permits and environmental analysis being a challenging part of the process. Restoration of land for an onshore wind farm is relatively simple due to a lack of operational waste product. Disposal or recycling of turbine blades and other materials will be required. Now come to offshore wind, which includes fixed bottom and floating offshore wind. Construction costs for offshore wind farms are higher than for onshore wind farms due to more robust design requirements for a marine environment and significant transmission assets needed to get electricity from the wind turbines to the shore. Construction costs are impacted by water depth and distance to shore of offshore wind plants, which influence the amount of materials required and installation time. Electricity production costs for a new offshore wind farm are higher than onshore wind due to higher capital and operational costs. However, plant output is typically higher than onshore wind due to stronger offshore wind resources. The capacity factor of offshore wind can be higher than that of onshore wind since wind tends to be stronger and more consistent over the ocean. Given proper conditions including weather, offshore wind plants have some ability to ramp up and down for certain durations and magnitudes and have been relied upon to do so in some places to support grid reliability. They can be shut down or turned out of the wind to reduce plant output if needed. Offshore wind plants are available to produce power only when the wind blows at sufficient speeds, which may not correspond with peak demand. Turbines must shut down at wind speeds exceeding their design range. The area required for an offshore wind farm is similar to that of an onshore wind farm with the same capacity. There is no water use required for power production at an offshore wind farm. Because there is no combustion involved in offshore wind power generation, there are no GHG emissions. Because there is no combustion involved in offshore wind power generation, there are no resulting air emissions associated with power production. Direct waste products. There are no waste products associated with power production from an offshore wind farm. Ease of permitting. Permitting for offshore wind is more complicated than onshore wind, requires more agencies and public comments, and may take several years to acquire all the necessary permits. Restoration of ocean area for an offshore wind farm is relatively simple and may result in new artificial reefs for aquatic life. Disposal or recycling of turbine blades and other materials may be required. Since offshore wind is a relatively new technology, end-of-life considerations may change once the first wind farms reach the end of their life.